reliability for some materials, right? In quantum materials, there are many new quantum states that can only become available if there are this heterogeneities exist. For example, defects in silicon carbide or diamond, they can give us very long coherent quantum states. And the interfaces in graphene nanoribbons can offer us topologically protected spin centers. And the spin frustration in some materials can lead to the formation of quantum spin liquid. And these states wouldn't be there if there wasn't heterogeneity. So realize the importance of heterogeneities in quantum materials. Our theme is aimed at providing an atomistic level understanding of heterogeneities. We want to see how they define and affect quantum states in order to enable new materials for application in energy or quantum information science. To study heterogeneities, the first step is to reveal the structures of heterogeneities. We want to see how the structures correlate with their properties, like electronic, magnetic, vibrational, and optical properties. And then in the second aim, we want to study the effect of heterogeneities, see how they affect the host environment, the host material, particularly the coherence entanglements of the quantum states in the material. And based on this understanding in the aim 3, we want to control heterogeneities or create new materials with rationally designed heterogeneities in order to tailor the energy conversion process for quantum information science application. We have organized a large team that consists of more than 20 PIs, 20 individual PIs. We are taking this co-design research approach. In the material synthesis stage, we want to control heterogeneities and manipulate heterogeneities. And then in the characterization stage, we use microscopy and spectroscopy approach to characterize the structure and the different degrees of freedoms of heterogeneity. And then our theory team provide with DFT type of calculations for the electronic structure. They can also model the interactions of quantum states. Moreover, they use ML approach to accelerate the simulation and the feedback to experimental effort. Here is an example to show how we reveal the structure of heterogeneities. Our team member, Jordan Hector, and his collaborators are using STEM. Basically, they are improving the resolutions of STEM, both in terms of spatial resolution and the energy resolution. They have found out they can use electron energy loss spectroscopy to detect isotopic shift of carbon-oxygen stretching modes. And based on that, they can label the molecules in the materials based on these isotopic shifts of the energy loss spectroscopy. And Jordan will talk more about this approach. To understand the effect of heterogeneities, Wang He Ko and our STM group has been using quasi-particle interference approach to study magnetic topology insulator, like manganese bismuth telluride material. And with this approach, we can visualize both the topologic surface states and also the box states by adding dopants to the material, for example, to include antimony substitution to the bismuth side. We can shift the Fermi level to the gap of band structure. That way, we can really visualize the surface bands. Moreover, by using thin films with different thicknesses, and we can visualize both the exon insulator state and also quantum anomalous Hall state at the edge of thin films. When he will talk more in his talk. And then to control heterogeneities for new quantum states, Merrick Kommer and our STM group have demonstrated we can grow quantum materials bottom up by using rationally designed molecular precursors. In this case, we grew graphene nanoribbons, which are atomically precise. In this material, the width is very well defined, and the end states are also atomically precise. In this particular case, each end is a superposition of spin up and spin down, and these two ends of the graphene nanoribbon give us a pair of non-locally entangled spin states. For future opportunities, probably most of you already know, we have this Quantum Nanoscience Center led by ONL. It's one of the 5 centers funded by National Quantum Initiative. And CMS, particularly our team members are playing a big role in this Quantum Science Center. Rod Moore will provide a glimpse at how we are working together to push the research envelope of quantum science. Another opportunity I want to mention, actually Karen already mentioned briefly, is this nanoscience material science infrastructure. And this is a new development led by Chris Rulu, and it's currently under development. It will combine the AI-guided synthesis platform with scattering-luminescence SEM and also spin-polarized STM. So we will be able to synthesize quantum materials and characterize the quantum states and quantum behaviors in the same system. In the end, I want to just summarize by showing this slide again. We are trying to understand heterogeneities and particularly understand their structures and their effects. Also, in the end, we want to control them to deliver new materials for new quantum functionalities. The ultimate goal is to deliver new understanding of heterogeneities. We also want to develop new capabilities so our users can use these capabilities to characterize the materials of their choice. So that's what I want to introduce about the theme. Let's say, if you have questions from our audience at this stage. Yeah, if you have questions, you can just speak out loud. I can. So if no question at this stage, I want to introduce our next speaker. Actually, the next speaker is a plenary speaker. It's Professor Zahid Hassan, Princeton University. Professor Hassan is a Eugene Higgins Professor of Physics at Princeton University. He has many titles and accolades. Among them are DOE E.O. Lawrence Award, and also the member of American Academy of Arts and Sciences. And today he will talk about the discovery of topologic magnets in 2D and 3D. Yes, you can go ahead and say it. You are muted, I cannot hear you.
Okay.
Okay, yeah, good.
Is it okay?
Yeah.
Okay, thank you, Anping, and organizers for giving me the opportunity to speak at this wonderful workshop. I was quite impressed by the facility overview at the Nano Center. It sounds wonderful, future of quantum materials lying there. So I'm excited about that. Okay, so I will talk about these topological magnets in 2D and 3D. More technically, it's about Charn, Weil, and Kagome magnets, and what is the physics frontier beyond that. So, but I will start with, since this is a very broad spectrum of audience, I will start with a 5 to 10 minutes introduction to topological materials as a field and where this field is going, at least from my point of view, and how sort of it started. And this way I will also introduce the conceptual framework. So this conceptual framework will help understand the later part of the talk, which is focused on magnets. Okay, so in last 10 years or so, I think, even 10 years ago when I was teaching condensed matter physics, I used to tell students that it's about metals, insulators, magnets, superconductors, and their symmetry broken or symmetry related variants, as you can see in Kittel or Ashcroft-Marmin book. And but last 10 years or so, that paradigm is significantly extended into new regimes, at least conceptually, not only just conceptually, but also in terms of real materials showing, exhibiting those new conceptual paradigm. So this started with the three-dimensional materials, the three-dimensional semiconductors or insulators, their topological variants, the topological insulators, topological magnets, topological semi-metals, and the number of candidates for topological superconductors, and also more recently their more interaction-oriented variants are also beginning to appear. So, so the distinction here is that to understand these phases of matter, understanding the symmetry of electronic states and crystals are not enough. You have to have a sense of the wave function space or Hilbert space topology, and how that Hilbert space topology is manifested in physical, electrical, and magnetic properties. So this also gave us a reason, good enough reason to reorient our experimental techniques to address these issues. So this last 10 years or so, that the experimental techniques have also been reorganized in a way to address this. I'm not going to talk a lot about techniques. It's going to be mostly about concepts and the materials realization and how to interpret the experiments. And I will, as promised, focus on magnets, not everything. So let me start out acknowledging my students and collaborators who are on the ground doing the real work. So the particular work I will be presenting is a collective effort of Ilya Belopolsky, Suyang Zhu, Jiaxinin, Goqing Chan, Sonia Zhang, and Guang Bian. And rest of the group members are also involved. So we are funded by DOE and also Moore Foundation to do STM, RPS, and theory. So our theory effort is led by Goqing Chan, and multiple postdocs and students are also involved. We collaborate with Xin Lin's group. Sample-wise, we, at least for this talk, we are collaborating with Ramon Shankar, Fengcheng Chiu, Jiangleng Zhang, Shuang Jia, Nitin Samarth, Claudia Filser, and a number of other groups around the world. And besides our Princeton lab, we also use facilities, primarily Lawrence Berkeley Lab and SLAC. I'm also affiliated with LBL. We also use, we have limited use of NSLS and also SLS, and staff scientists there are a wonderful resource for us and fantastic collaborators. Okay, it's a lot of collective effort. Okay, so let me briefly introduce the concept. This is relevant for a large number of quantities, large number of experiments. So I would say this, it all started with the experimental discovery of quantum Hall effect. In a clean enough sample, you apply a magnetic field strong enough that the cyclotron orbits, the Landau or cyclotron orbits or the Landau levels that create make the bulk insulating, but the skipping orbit scenario allows you to understand, even though the bulk is insulating, there can be conducting edge states. So this is kind of a simple-minded interpretation of the quantum Hall effect. Now, if you want to represent quantum Hall effect in energy momentum space, in a dispersion relation sense, then that means you have a gap in the bulk energy spectrum. But on the edge, there is a gapless edge state, chiral. It's one direct, the magnetic field direction sets the chirality of the edge state. So you have a branch like this, single branch. And this is topological. When you calculate Hall conductivity using Kubo formula, then you will see that this quantization depends on a quantum number associated with this. Hall conductivity is actually a topological quantum number, a Chern number. So it's this state, this ground state is described by a single invariant, or a Chern number, TKNN number, if you want to call it that way. So this is the first example, at least in condensed matter physics, of a topological state in a multi-particle system. So decades later, people considered, what if we take 2 copies of the quantum Hall state, and the spin up and down, and put them together? Is there a natural interaction in the solid that allows us to do that? It turns out the relativistic term, the spin orbit term, which is relativistic in this case, it's like a velocity dependent field. It allows you to do that. So the spin orbit term kind of plays the role of field up, field down. So then you have so then you can think of it as 2 copies of the integer quantum Hall state. So then you have a chiral edge state, like one unidirectional one way, and you have another edge state the other way. So in this picture, it would be going the other way. So now, if this thing can superpose, there is no real magnetic field. There is spin orbit. It's kind of like a magnetic field, up and down, both in superposition, acting on the electrons. So then this topological state is also described by one invariant, but it's not a Chern invariant, but you can call it a Chern parity or Z2 invariance. Its parity, it has 2 values. So instead of a Chern number, you have a parity, Chern parity here. It's also single invariant. Either it's topological or not, but there's no higher order thing, Z2 Z2 state. So now, if you focus on the energy momentum dispersion relation, then you see that what is new compared to the quantum Hall physics is that now, because of time reversal invariance, now there is no magnetic field. There is this protected crossing. So, and this protected crossing is linear. So this is a Dirac fermion. It's an emergent or effective Dirac fermion. So then this low energy excitation would be described by the Dirac equation, which, so then much of the QFT physics, quantum field theory type physics, could be realized in systems like that, because these Dirac fermions are very stable. So this is how the Dirac fermion and topology connection appeared in condensed matter physics only recently, even though quantum Hall physics existed from the 1980s, right? So this new topological state, where they're described by Chern parity as opposed to number, and then associated with Dirac fermions, Dirac equation, and quantum field theory, it created an enormous excitement. A lot of new physics is possible beyond the quantum Hall physics. Now, there is additional reason to be so much excited, at least experimentally. In fact, both experimentally and theoretically, because now we can see that all the 2D topological states, say a Chern insulator, this is like integer quantum Hall is like the original Chern insulator, and the Z2 or quantum spin Hall insulator. These are kind of like, there is some sort of, you can describe in some sort of generalized Hall physics, Hall effect type of thing. But in 3D, there is a topological state that cannot be described by Hall effect type of thing from an experimental point of view. And this new state is what was originally called topological insulator, because now you cannot use the Hall effect of this, Hall effect of that, Hall effect of this, or anomalous Hall effect, none of that. So this is really new state. It's more clearly understood in a purely from topological point of view that you need 4 invariants to describe this new state. So it's not, there's no Hall effect associated with that. So this is one excitement, conceptual. The other excitement is that this state is possible in 3D materials. You know, the 2D materials, to observe Hall effect, there's a lot of purity issue, sample issue. You need a very clean sample, all sorts of things. But when you go to a 3D, you found a topological state that is a tremendous experimental excitement. So this, and also you can see the name. Now, these things are called 2D topological insulators, but the name originated from the 3D topological insulator because it could not be described by a Hall thing. But 2D always described by some sort of Hall thing. So for the rest of my talk, when I talk about topological insulator, I will mean 3D topological insulator, because this is the origin of the term. And then if I have to go to describe some Hall effect or something, I will call these things some sort of Hall effect or Hall insulator. Okay, so now you have Dirac fermion on all surfaces, odd number of Dirac fermions on all surfaces, and their spin momentum locked. Now the challenge is, how do you, here you could probe these things by doing transport, right? I mean, in fact, they were discovered by transport. Either you call it quantum Hall effect or quantum anomalous Hall effect. It's all transport effect. Hall effect is a transport effect. But these invariants are not connected to transport effect, at least not directly. So this is the experimental challenge, also a conceptual challenge for, especially I experienced that with experimentalists in about a decade ago. They had difficult time for some reason to understand that you cannot do a transport effect and discover a 3D topological insulator. It's just not conceptually possible. So people keep saying that why transport is not happening. It should not be happening because there is no transport that can directly couple to any of the topological invariants which define the state. So it took the scientific community to fully understand why that is so. Of course, it's obvious in the theory that is not. So these invariants do not lead to a quantized transport. So if you are doing transport, you'll not be able to measure the topology. You'll have indirect signature, but not a direct measurement of the invariant itself, which is in clear contrast to the quantum Hall effect, where you do transport, you measure the invariant. So that's why for Hall-like effect or quantum Hall 2D topological insulators, transport is crucial because it you couple transport couples directly to the topological invariant. So there is one way of measuring one of the invariants by doing magnetoelectric effect. This is also this is a susceptibility or second order green function type effect. This is a response function effect. That way you can measure one invariant, but you cannot measure all four. But in 3D topological, in 3D, there are at least 15 different types of topological insulator. One is the trivial insulator. So how do you know that which 3D topological insulator you realize? These are much more difficult challenges than doing transport. Okay, so then what we were doing, so we argued that, so these are topological invariants, and topology is about bulk boundary correspondence. So we have to measure the electronic degrees of freedom inside the bulk and also on the boundary. Then if we can connect the bulk and boundary measurements, all degrees of freedom of the electron will have some sort of access to these order parameters, topological invariants. So that means we have to do spin resolve, momentum resolve, energy resolve measurement on the edge, on the boundary, and also on the bulk. Then that exhausts the electronic wave functions have those are all the quantum numbers electron has, right? So it has energy quantum number, momentum, and spin, and it can live on the edge on the bulk. If we can make a contrast, then we'll have a full access to the topology, and that is exactly what we have been doing for last 10 years or so. In the process, we have to introduce subroutines. We did not invent RPES, of course. RPES existed even before Einstein. Einstein got his Nobel Prize by explaining RPES. But as the new scientific problem comes at hand, we have to reconfigure how to do the measurements to address certain phenomena. So all those methodologies that we introduced, I'm not going to review them. They're introduced in these 7 papers and reviewed in this Review of Modern Physics article back in 2010. You can find more details in my website if you're interested in instrumentation innovations or the experimental conceptual innovations we introduced. They're there. I'm not going to review that. Okay, so let me give you a quick one quick example how topological invariance is measured in spin RPES. For example, if you take bismuth selenide and bismuth telluride, they're insulating. When Fermi level is inside the gap, you can see there is no bulk band or anything. You have a Dirac Fermi surface, circular Fermi surface. Fermi level is here. You can achieve that under UHV. We can do that by in situ chemical gating. And then you do spin resolve measurements. You see that K, if you assign K plus to spin down, K minus is up, and no matter how which diagonal cut you take, there is time reversal symmetry. So that means now you can see that on the surface you have a single Fermi surface, and you consider what is the Bary phase associated with this Fermi surface. This you can go to the original definition of Bary phase, which is, for example, taking a quantum quantity in some parameter space and rotate 360 degree, or I mean, you just complete a rotation and see how much phase it picks up. So it spin RPES automatically allows you to do that old theoretical construction. So you imagine you're taking, as you do this measurement, you're taking spins in momentum space, that is your parameter space now, and go around 360 degree, you see that you pick up a pi phase, right? Because electron is spin half. If you move a 360 degree, then you don't recover the full wave function, you'll get a negative sign. So that means you pick up a phase of pi if you do the Berry phase definition construction on the spin RPS data. So topological invariant is the Berry phase electron picks up divided by pi, so it's 1. So that means what I was saying, that this invariant in that compound is 1, it's not 0. And it should be die-valued 0 or 1. So then it's topologically non-trivial. Okay, so this constituted a determination of topological invariant, but you also have to prove if it is topological, it should be the same, it should remain the same as you tune the chemical potential across the gap. So no matter where you place your chemical potential, it should be the same. So this is how this was done, that parameter space construction below the Dirac crossing, the spin chirality in momentum space will reverse, but the Berry phase remains the same. So in other words, the Berry phase is invariant no matter how the spin chirality, even if it is changing, as long as you are inside the gap. But if you're outside the gap, then the spin from the bulk bands will contribute, then that will destroy your pi-Berry phase. What does that mean physically? It also means the electron moving to the right, down, moving to the left is up. So there is a spin momentum locking no matter which direction you cut. And this is true for all surfaces. And there is at least one pair like that. So what does that tell you? That this type of diagram tells you that in the absence of a magnetic field or anything that breaks time reversal, if the electron is trying to take a U-turn, then there is no state available, because this is spin up state, but there is no state available, up state available here to scatter to. So it cannot scatter. So that means it cannot take a U-turn. So absence of backscattering. This is also seen in STM QPI, SPM QPI, the absence of backscattering. So that means in topological insulators on the edge or on the surface, direct backscattering is forbidden, side scattering is not. So another amazing thing about these 3D topological materials is that you can, these topological properties that I described so far, they all survive up to 300 K. So these are room temperature topological phenomena. And so this is quite remarkable because there is no magnetic field. There is no, so you are at room temperature, no magnetic field. This is unprecedented. Before this work, there was no demonstration of room temperature topological phenomena without a magnetic field. So quantum Hall physics is always at very low temperature, and you need a magnetic field. So getting rid of the requirement of low temperature cryogenics and magnetic field creates enormous experimental opportunities for people to have access to topological phenomena. So it's also important to explore their room temperature properties for a device application, for future applications. So these are all, in my view, these experiments collectively demonstrated why this field should be further pursued. And indeed that happened. Shortly after we demonstrated these properties, this is my slide from 2011. You'll see all the papers are stuck at 2011. And a lot was already happening. There was superconductivity, phase transition, quantum Hall effect, Landau quantization, quantum anomalous Hall effect effort, at least initial reports, and magnetic topological insulation. There are claims of topological condoinsulators. So the field exploded shortly after that, because these materials were demonstrated to be capable of doing these things. So all these things, I'm just citing what happened in bismuth-based topological materials. Okay, so then beyond that, where is the field converging? What is the further future of the field that was being considered back then? So I would say there are two major thrusts was can we realize half fermions? Because now we have access to Dirac fermions, real Dirac fermion, single Dirac fermion, unlike graphene. Graphene has 4 Dirac fermions. On topological insulator surface, 3D topological insulator surface, you have a single Dirac fermion. So they're like 1/4 of the graphene. So once you have a single Dirac fermion, you can think how to split. If you split Dirac fermions in 3D, you'll get Weyl fermions because Dirac fermions in UFT, they are made of a pair of Weyl fermions, chiral and antichiral. And you can also think of other solutions to the Dirac equation, like real solution to the Dirac equation, meaning that Dirac fermions that are their own antiparticle. So those are known as Majorana fermions. They have their real solution to the Dirac equation. Since they're real solution to the Dirac equation, then if you take their complex conjugate, you get the same thing. That's why Majorana is its own antiparticle. So these ideas fell from the Weyl and Dirac, Weyl and Majorana are half fermions. So there were efforts how to realize them. Okay, so what topological insulator brought us, in my view, is new directions, new possibilities, opportunities, both conceptually, theoretically, conceptually, and material search and materials engineering, including nanoscale materials engineering, to realize these particles and make use of them for various things, maybe for qubit, for quantum devices and effects and a lot of things. So this continues today, right? So as I said, that I'm not going to review all that we have been doing. I'm just going to be talking about what are the recent developments, what are the developments in magnetism, topological magnets. So just as topological magnets started as earliest topological insulators, there's this 2008 archive paper we showed this. You dope the surface or the bulk and you can break the Dirac fermion, introduce a Dirac mass. And this is also reviewed in my RMP in 2010. This figure is from RMP. So in other words, the effort to make magnetic topological insulators was even reviewed in 2010. Okay, so materials qualities were not that great, but conceptually they were demonstrated that the Dirac fermions opens a gap. Okay, so then subsequently we introduced a number of experimental methodologies to demonstrate, to realize Chern insulators. How do you know a magnetic topological insulator has a Chern gap, or any topological material realizes a Chern gap? So one of the diagnostics we applied that you could explore the dichroism, circular dichroism on the surface, and also see whether the dichroic signal hysteresis is correlated with the gap we observe. So in other words, we are trying to probe whether the gap is artificial, artifact, or real magnetic gap. So the idea is if dichroism and hysteresis is not there and you see a gap, then you're in trouble. That cannot be magnetic gap. And also gap, what is the temperature dependence of the gap? So is it surviving well above the magnetic ordering temperature or not? So we found that in addition to those diagnostics, you also have to do spin ARPES to see and probe the spin texture near where looks like there is a gap. So, and then there are various possibilities. So So only we see that the true magnetic gap will have this type of hedgehog type spin texture. In other words, if you place your Fermi level here, then you should see a spin polarized Fermi surface, and this gap should be closing as you raise temperature. But there are also extrinsic gaps. For example, if your thin film is too thin, then it could create a gap, but this will not create a hedgehog Fermi surface spin texture. So then you will know that this is a gap in a magnetic or even non-magnetic topological material, but it has nothing to do, it's not a Chern gap. Furthermore, you can be more rigorous. You can systematically gate the system, chemically gate the system into the magnetic gap and see watch Berry phase tunability that at some point the Berry phase will be totally destroyed. So with all these diagnostics, we figured that this is a signature of a Chern gap. So in other words, this is a Chern magnet. So, or it is a Chern insulator. For example, this is a Chern insulator. We demonstrated that in this Nature Physics paper in 2012. So now, can we find other evidence that this is a Chern insulator? One transport evidence is that you will have quantum anomalous Hall effect. All these were done in UHV. We cannot do transport on this Chern gap magnet. So we could not demonstrate that this Chern insulator shows quantum anomalous Hall effect. So that was the limitation. So then, but it is a Chern insulator. There is no other way of explaining this thing. I mean, even if you do transport measurement and call something quantum anomalous Hall insulator, that's also you're connecting to theory. That's not experiment by itself demonstrating that. So then we wanted to see deeper insight. So one possibility we looked is that how about in other materials? So because in this material it's so difficult to do transport under UHV, even though this is a Chern insulator. So then we sought other materials where there may be a Chern gap, and we can use our technique to figure out whether it is a Chern insulator or not. So one such material that we applied these ideas is this iron tin compound. And then it is a Kagome system, so it has a flat band and also a magnetic gap. So if you apply if you have a magnetic layer, then this Dirac fermion will create a Chern gap. And then we can do STM or ARPES, and then I'm going to jump into something beyond the Chern gap. So this system looks like this is strongly correlated in the sense that even though it has a twofold electronic quasi-particle interference pattern, which suggests that there is a nematicity beyond its crystal structure. So it's in the electronic channel, which we can control with an magnetic field. And this is the first example of an electronic nematic system where you can control with a magnetic field. I don't know of any example of that. If you apply a strong enough field out of plane, your crystal symmetry recovers. QPI is now 6-fold so that means this is a Chern magnet with a very strong interaction that it's really pushed into a many-body physics regime. Okay, so but apart from the many-body part, which makes it more complicated, so let me review what was happening. In 2012, we demonstrated this Chern gap, but we could not detect edge state or do Landau levels in transport. A year later, Chikun Shui group in Tsinghua, they were doing chromium doped bismuth. They observed the quantum anomalous Hall effect at very low temperature. The gap is very small, and it's hard to do spectroscopy to find out what is the microscopic that is going on there. So, so in this case, we could prove that there is a Chern gap, but there's no edge state. So in the Kagome materials, we could see that there is Chern gap, but edge states were not that accessible. And there was also work by MIT group Tchaikovsky, they just found anomalous Hall effect. So then the goal around 2008 remained that identify or make a 2D Chern magnet in the quantum limit where edge states are accessible, the Landau levels are accessible, and Chern gap is large, more than 25 millivolts, so that you can have a room temperature Chern insulator. That is the goal. And the chromium doped bismuth selenide stuff is a very low temperature, and you can hardly do any spectroscopy to actually learn what is going on in that system, or is there any many-body effect? Is there nematicity, or what is the Luttinger scaling? Is there Luttinger liquid state there? None of those can be addressed there. So we need a new material platform where these things could be done. And also in the interacting limit, can we explore many-body physics? So guided by our 10 years of experience with Chern insulators and their spectroscopy, we discovered a new class of materials which are Chern magnets with a much larger gap. So this is 166 compound. This was reported in Nature last year. So in this system, it's extremely clean. This is grown by Shuang Zia's group in collaboration with us. We showed that in this series, terbium has the best, it gives the largest Chern gap because it has out of plane moment. In some other rare earths, you have some Chern gap, but these things have interesting magnetism, a topological semi-metal type of thing, but not necessarily. So largest Chern gap should be in the terbium system, so in 166 compounds. So now we can see that of all the Kagome magnets we studied or other people studied with STM, we can see that this is the cleanest. These other famous Kagome magnets like Mn3SN or iron-tin that we studied before, these are all data from our labs. But this is the cleanest system. So we were excited that if this is so clean, maybe we'll be able to see edge state so in the quantum anomalous Hall regime, and the gap is large. So first step is to see the Landau quantization. So with STM, the nice thing is that you can selectively look at the Kagome plane and the non-Kagome plane. So when we cleaved and looked at with STM, look at the Kagome plane, then we see when we apply a field, there's a very clear DOS modulation. And in the non-Kagome plane, similar field, similar condition, but there's no DOS modulation. So in other words, this DOS modulation is associated with the Kagome plane's electronic structure. And then we can look at the Landau fan in great detail, look at the Landau fan dispersion, and we can clearly see the higher Landau levels are nonlinear, which is signaling Dirac physics, as opposed to parabolic linear, which would mean parabolic band. So non-linear Landau levels suggests you can fit with a massive Dirac fermion. So we find a wonderful fit to this massive Dirac fermion picture. And then that way we can estimate where is the Dirac node with respect to the chemical potential. That's about 130 millivolts. And the gap is large. So this is 34 millivolts. And that's wonderful because we just wanted something more than 25 millivolts. So this is very large gap. And now, so far, based on this data set, I cannot tell whether it's graphene. Graphene also has nonlinear Landau fans, right? So it only tells you there is massive Dirac fermion. That does not necessarily tell you it's Chern insulator, right? So now we are left with the task of proving that this Dirac mass is a Chern gap. In other words, it's topological. So if this is topological, then there should be bulk boundary correspondence. This is what we demonstrated extensively using spin RPES. So in other words, inside the gap, there should be a chiral edge state. Is there a chiral edge state? But how do we know where is the gap? So we know that from this fit, we know that about 130 millivolts Fermi level the gap is robust. I mean, the edge state should be robust. So when we scan the step edge, and only around 130 millivolts, we see that the step edge is lighting up, meaning that this is a conducting channel. We also check that this is backscattering free. So that means there is a chiral edge state here. So in other words, and these numbers match up. This 130 we learned by detail fitting this thing to a massive Dirac fermion. So that means this massive Dirac fermion is actually a Chern topological gap. So we don't see that. We also check that on a side cleave, we don't see that. So now all these numbers, we can also get many of these numbers by fitting transport. So this is anomalous Hall transport, anomalous Hall resistivity. This is done by Shuangzi's group. And then if they fit their transport data, they get the numbers they get, that the gap is about 34 millivolts and the Fermi level is about 130 millivolt away from the Dirac node, which is in fantastic agreement with what we got from STM. So this is enormous, somewhat unbelievable agreement between STM and transport. It doesn't always happen, but this is quite remarkable. So now we know, this is what I was saying, that you can observe in some sample, some quantum anomalous Hall effect, but you don't know the microscopics. You don't, how do you engineer it further? So here, since we know all the microscopic, we know how much to engineer this further to take it to the quantum limit. So we find that if you place about 10% nickel or something, then you can drive it to the quantum limit. So we are working on that, but this is, in my view, is a room temperature, potentially room temperature Chern insulator, where you can see chiral edge state and all that stuff. So this is a candidate material to engineer further to realize a room temperature quantum anomalous Hall effect. That has not happened yet. There's a lot more to be done to engineer this material, perfect this material, but it has the microscopic electronic structure, spin orbit strength, and topological strength, topological gap strength to be a prime candidate for a room temperature quantum anomalous Hall material. Okay, I don't have a lot of time, but I'll briefly introduce. So that was our 2D topological magnet discovery. Now I go to the 3D topological magnet discovery. This also has ancient roots. We were working on topological insulators, considering how to drive a topological phase transition. So at the topological phase transition, you realize a 3D Dirac fermion, right, in the bulk. So our algorithm was, since we know how to do Chern gap and all that, so if we realize a 3D Dirac fermion by driving a topological insulator to a normal insulator, at the inversion point, we have a 3D Dirac fermion. Then if we just if we magnetize it, we'll get a Weil fermion. So that will give us the simplest form of 3D topological magnet. We're interested in 3D topological magnet. And these ideas are described in both our theory and experimental papers starting 2010 and 2011. This is also Suyang-Zhu's science paper in 2011, where we showed that there's a 3D Dirac semi-metal at the inversion point of when you drive a topological insulator into a normal insulator. Why were we interested in that? Because we were working on 3D topological insulators way before that, right? So then back then I asked my students, Ray, to magnetize this Dirac critical point so you can get high Weil fermion. And I asked Neupen and Shankar to magnetize these compounds. And I asked Suyang Zhu and Ilya Belopolsky to search in the database to find eye-broken analogs of this thing. So it turned out that magnetizing Ray, Neupen, and Shankar's project was very complicated because it's very complicated material science. on the other hand, Su Yang and Ilya's project were searching in the database, which was somewhat easier. So we use this algorithm, materials finding algorithm that's shown in our paper, theory paper in 2014. So you start with a topological insulator, close the gap. So you have close the gap in 2 places. You get critical points here. And then if you break some symmetry, so this is a Dirac point. If you break some symmetry, then you must split the Dirac point. In QFT or Dirac equation, you know that only way to split a Dirac fermion is Weil fermion. So you get Weil fermion. So now since you have to split, then your Fermi surface will also get split. These are the Fermi arcs. So these are the Weil fermions and these are the Fermi arcs. So since we knew, we were researching a lot how to find topological insulators one after another, we use this route, how to go from a topological insulator to a Weil fermion or Weil semi-metal. So this is our prediction. And also we gave a materials algorithm how we found this by.
Okay, can we wrap up in a couple minutes?
Yeah, I'm almost done. So then in the experiment, we did not actually compare with our theory either. Then we invented experimental methodology that in RPS, if you do a loop cut, instead of comparing with somebody's calculation or our calculation, if you find chiral edge modes, this is what I was talking in the context of Chern insulator, in a momentum space cut, then you will see if you have chiral edge modes, then that's like this is like inside the Weil semi-metal, you have a cut that is like a Chern insulator. So in this case, you have 2 chiral edge modes because you have multiple Weil points. So then we did low energy RPS and high energy RPS. In low energy RPS, we see these arcs. In the high energy RPS, we see these dots. So these dots are Weil fermion dots in the bulk, and these arcs terminate on the Weil fermion point. So this is the bulk boundary correspondence, that this is on the boundary, this is in the bulk. So this is topological. So you can see that I did not use any calculation anywhere, comparison with band structure calculation or anything, DFT or anything, to prove topological Weil fermion. So we did that without. So this we used the methodology in an earlier paper that was 2014, also Su Yang's science paper. So where we showed a double Weil fermion and arc, and this methodology, then we use this the split Weil fermion, and then there are a number of other groups worked on things that were similar to this paper, earlier paper. Okay, so then we can, but that was non-magnetic. Then we have a theoretical prediction based on those set of ideas, it's published in PRL, where you could find a magnetic Weil fermion. So this is cobalt, manganese, gallium. I don't think any other group theoretically predicted that, even after us. So then we went through that same process, that can we prove topology without comparing with band structure calculation? We did that, and then we did more. We said that if we take this Weil loop topology and from RPS and predict what should be the Berry curvature field distribution, then we can predict transport, like anomalous Hall transport, because if I know the Berry curvature field distribution, I know everything topological about it regarding transport. So then we use that to predict that this compound, this 3D topological magnet, should have anomalous Hall conductivity on the order of 1,000. And the transport was done later by Kaustav Manna, and then he found 870. So this is a remarkable thing that RPS could predict transport. So I did not show many examples, but we are now combining spectroscopy, advanced spectroscopy and transport to show that the correspondence, because bulk boundary is enough to prove topology, and transport gives additional signature, which is useful if you want to make these materials useful for device application. So So then this is my summary slide. We showed 2D Chern magnets starting from 2012. And then we showed that the Kagome magnets are better. That's how we found the room temperature Chern insulator in 2020. And then we were also searching for 3D topological magnets, and that led to Weil fermion and Weil loop topology magnetic stuff. And on the way, we found a number of quantum many-body effect in these topological materials. That is another goal in the field. So there is, I think, there's a whole lot to do, and there's a lot of excitement in the field. I did not go over many details, but we have a number of review articles that gives you the details. Most recently, we have 2 review articles in Nature Reviews, one in Nature Review Materials, one in Nature Review Physics, that reviews the last part of the talk, which is not listed here. Thank you.
Thank you, Rahid, for the excellent review of the topologic magnet field. So are there quick questions in the audience? I don't seem to
I have a quick question.
Yeah, go ahead.
Zahid, I think you show this magnetic field dependent of this STM, and then seems it imply the magnetic field is along the parallel direction. Is that right?
Which one?
The back a couple. Let's see.
Yeah, yes, it is in the parallel direction, yes.
And then you showed it up to 9 Tesla.
Yes.
Oh, okay. Well, the vector field reached 9 Tesla. That's very unusual.
Right. Yeah, our system goes up to 9 in the 9, and we have the parallel field is like 2 Tesla.
No, but then you have this thing you try to see, you see a lot of stripe phase form, and then when you change the magnetic field, at 1 you show it as 0, and then at 9 Tesla, I just wonder if that field is, I forgot which one that you show.
No, in the parallel, I don't think I showed anything more than 2.
Okay. Thank you.
Right.
Yeah.
In the perpendicular, I showed up to 9.
Oh, okay. So that 9 Tesla is along the perpendicular direction.
In other perpendicular direction, yes.
Okay.
Yes.
All right. Thanks.
Okay, thank you. So if there are no more questions, then please our time. Let's move on to the next talk.
Okay, thank you.
Thank you. The next talk is going to be given by Professor Qizu Chang from Penn State University. Qizu is an assistant professor of physics in Penn State University. His honors and awards include Alfred Sloan Research Fellowship and the MIT Technology Review Certified Innovators Under 35. So today his talk is about tuning the Chern number in quantum anomalous Hall insulators. Take it over.
Okay, thank you. Can you see my screen now?
Yeah, it's good.
Yeah, thank you. And I'm Qizu Chang from Penn State. And first, thank for the kind invitation from Anping to. I'm very happy to give the talk here. You know, today I will talk about our recent work about the tuning the Chern numbers in quantum anomalous Hall insulators. Here is the outline of my talk. I will first give a brief introduction about this kind of the quantum anomalous Hall effect and the topological insulator. I will show you why we use topological insulator to realize the quantum anomalous Hall effect. And we know that in 2013, with many efforts, we are the first to observe the quantum anomalous Hall effect in chromium-doped topological insulator films when I was a graduate student in Tsinghua. And more recently, my group at Penn State fabricated the magnetic TI and TI multilayer structures and realize the high chain number quantum anomalous Hall effects. And by controlling the chromium doping concentration in the magnetic TL layer or changing the thickness of the middle TL layers, we can tune the chain numbers in this kind of the fixed sample configuration. If I have time, and I will give a little bit introduce our recent progress along this direction about the chain number and quantum phase transition between the C equals to 1 and C equal to 2 quantum anomalous Hall insulators. And finally, I will give a brief summary. So let's start from the Hall effect. You know, when the current flows through a conducting materials, which is in a perpendicular magnetic field, the charge carrier will be pushed towards to the two sides of the sample by the Lorentz force, and a transverse voltage will be formed. And this effect, we call it Hall effect. And this voltage, we usually call it Hall voltage. And the Hall effect was first discovered by Edwin Hall's in the 1879. And this is the Edwin Hall's the original data on the gold leaf. And we notice that the Hall effect it has been widely used to identify the carrier density and the carrier mobilities in the conducting materials. And about 100 years later, the quantized version of the Hall effect called the quantum Hall effect was discovered by von Klinsing. And in the quantum Hall effect, we can see that at high magnetic field, the Hall resistance is quantized and the longitudinal resistance becomes 0. So the quantum Hall effect is usually observed in two-dimensional electron gas subjected to the low temperature and high magnetic field. So we will naturally ask one question: can we realize this kind of the quantum Hall effect without the need of the external magnetic field? So the answer is yes. This kind of the quantum Hall effect, we call it quantum anomalous Hall effect. So let me introduce the quantum anomalous Hall effect. You know, this is the Hall family. There are three basic members: Hall effect, anomalous Hall effect, and spin Hall effect. And their quantized version, we call it quantum Hall effect, and quantum anomalous Hall effect, and quantum spin Hall effect. Quantum spin Hall effect is just the 2D topological insulators in his talk just introduced. And today in my talk, I will focus on this kind of the quantum anomalous Hall effect in the magnetically doped topological insulators. We notice that in the quantum anomalous Hall effect, at zero magnetic field, the Hall resistance is quantized. And at the same time, the longitudinal resistance becomes 0. And we notice that in this kind of the quantum anomalous Hall effect, if the longitudinal resistance is finite, the Hall resistance must be less than E squared or H over E squared. And in the quantum anomalous Hall effect, at zero magnetic field, when the magnetization up, the chiral ideal state goes this way. When the magnetization down, the chiral ideal state goes the opposite way. So that means the chirality of the ideal state depends on this kind of the magnetization of the sample. So I like the quantum Hall effect. For the quantum Hall effect, we notice that which started from the experiment, and later the theory tried to explain this kind of quantum Hall effect. For the quantum anomalous Hall effect was first predicted by Duncan Haldane in the 1988. And the Haldane's model was based on this kind of the one layer of the carbon atom. And today we usually call it graphene. So on this kind of the graphene in a periodic, this kind of the magnetic field, but without this kind of the net flux. And Haldane took the nearest neighbor hopping and the second nearest neighbor hopping in his calculation. If the second nearest neighbor hopping T2 is 0, so that's there will be two Dirac coins at the corners of the Brillouin zone. So this is just the band structure of the graphene. So when the phase phi of the second nearest neighbor hopping is included in the theoretical calculation, the time reversal symmetry of the system will be broken and a gap will be open at the Dirac point. If we could tune the chemical potential into this gap, we will realize the quantum anomalous Hall effect. But we notice that in the graphene system, due to this kind of the very weak spin-orbit coupling, we could not realize the quantum anomalous Hall effect in graphene based on the magnetic doping. So on the other hand, the quantum anomalous Hall effect can also be considered as the quantized version of the anomalous Hall effect. The anomalous Hall effect can be easily realized in the ferromagnetic materials. So the quantum anomalous Hall effect can be just, if we could quantize the anomalous Hall effect in the ferromagnetic material, we can still realize the quantum anomalous Hall effect. So in the 1954, the Kemplers and Latinger were the first time to thought the anomalous Hall effect in the ferromagnetic material is intrinsic, is induced by the energy band of the materials. And when the Barrett language was developed in the 1980s, the Hall conductance actually can be calculated by this kind of equation. Is E squared over H times this kind of the integral of the Barrett curvatures in the first plane zone. And the integral of the Barrett curvatures actually equals to 2 pi times an integer number. This integer number is just, we call it in the ferromagnetic material, we call it a chain number. And this, if we based on these two equations, we can get the Hall conductance is just E squared over H times C. You know, from this equation, if we could realize quantum anomalous Hall effect, C, if C is non-zero, we could realize the quantized sigma xy. You know, from this equation, we can get the two conditions for the realization of the quantum anomalous Hall effect. One is C is non-zero. C is non-zero. Today we call it the material with the inverted band structure. We can also call it topological materials. And for the second is this material must be a ferromagnetic material. This is just a ferromagnetic insulator because it's quantum anomalous Hall insulator. And but in reality, you know, the Haldane predict the quantum anomalous Hall in the 1988. But in reality, it's very challenging to find this kind of the ferromagnetic insulators with non-zero chain numbers. So there in the following 20 years, a little progress has been made for the realization of the quantum anomalous Hall effect until in the 2006, the discovery of the topological insulators made the search for the quantum anomalous Hall effect become practical. So now let me a little bit introduce the topological insulator because the head just very comprehensively introduced this kind of the topological magnet and topological materials. So this is a band insulator. You know, this is conduction band and this valence band. If the strong spin-orbit coupling is introduced into this band insulator, the conduction band and the valence band will be inverted and a linear dispersion in the surface state will be formed between the conduction band and the valence band. So if we could, for this kind of the 2D topological insulator has been realized in the real materials and can be clarified in 2D topological insulator and 3D topological insulator. And 2D topological insulator was first realized in the mercury telluride quantum wells and later realized in the indium arsenide and indium antimony and quantum wells, and also in the more recently in the 1D primer tungsten telluride monolayers. And for the 3D materials was first discovered by the head in the bismuth antimony compound and also in this kind of the bismuth selenide family materials. And in my experiment, we were using this kind of the bismuth selenide family, also we call it 3D topological insulators for the realization of the quantum anomalous Hall effect. So let me show you why we, you know, obviously for this kind of the topological insulator already satisfied the first conditions for the realization of the quantum anomalous Hall effect because there is already inverted band structure. So the second condition is we need to introduce the ferromagnetic orders into topological insulator. So this is the topological insulator. Is this Diac surface state is protected by the time reversal symmetry. If we could introduce the ferromagnetic order into topological insulator, you know, a magnetic exchange gap, very small gap is just milli-eV corresponds to the Q temperature of the material. It's milli-eV, a gap within the bulk gap will open at the Diac point. So if we could tune the chemical potential into this magnetic exchange gap, we will realize the quantum anomalous Hall effect. In the past 15 years, most of my work was based on this kind of the magnetically doped topological insulator systems. In my PD, I did a lot of work to explore this kind of the quantum anomalous Hall effect, and I tried most of this kind of the transition metal in the periodic T-balls to dope this kind of the topological insulator bismuth selenide, bismuth telluride, and antimer telluride. We found there are only two elements can induce the anomalous Hall effect at a zero magnetic field, and chromium and vanadium. And for the chromium doping, you can see here for the chromium doped bismuth selenide, actually in the transport, there is no hysteresis. So this is a paramagnetic property. So we could not realize the zero magnetic field quantum anomalous Hall effect in chromium doped bismuth selenide. And in chromium doped bismuth selenide, we actually in the upper measurement, we could also see very large this kind of the gap at the Dirac point. But I think that kind of gap is not induced by magnetism in the samples. And from the transport, we can see that in this kind of the chromium doped bismuth selenide, actually there are some clusters inside. It's not random doped, chromium doped, and uniform doped chromium in this kind of the bismuth selenide. And for chromium doped bismuth telluride and chromium doped antimer telluride, we could realize the anomalous Hall effect at zero magnetic field. And the good news here is for this one, chromium doped antimer telluride is p-type, and for chromium doped bismuth telluride is n-type. So in our experiment, we mix this kind of the chromium doped bismuth antimony telluride for the realization of the quantum anomalous Hall effect. So we tried many samples, and in 2013, we were the first to realize the quantum anomalous Hall effect in the chromium doped bismuth antimony telluride. And this is the magnetic field dependence of the Hall resistance and longitudinal resistance at the charge neutral point. If we plot this kind of the zero magnetic field Hall resistance and longitudinal resistance as a function of the gate, we can see that at the charge neutral point, the Hall resistance is quantized. At the same time, the longitudinal resistance approach to zero. So this kind of the phenomena marks the discovery of this kind of the quantum anomalous Hall effect. So before moving on, let me see a few words about the special eddy state in quantum anomalous Hall effect. We notice that in this kind of the toy model, in this kind of conventional conductors, there are 4 degrees of freedom: spin up, spin down, and right Moore and left Moore. So impurities in this kind of the materials can backscatter the right Moore to the left Moore and give rise the electrical resistance. But in the quantum anomalous Hall effect, there is only 1 degree of freedom. It's just the spin polarized eddy state. And this kind of the eddy state, we usually call it Carroll eddy state. And the electron in the conventional material looks like the electron, the bus and the cars in this kind of the traffic jam. So, and the electrons in the quantum anomalous Hall effect just looks like the traffic on this kind of the highway. So the eddy state of the quantum anomalous Hall state give us a very good platform for the next generation of the energy efficient electronic and spintronic device with the low power consumption. And in addition to the C equals 1 quantum anomalous Hall effect in the chromium doped TI system, the zero magnetic field C equals 1 quantum anomalous Hall effect has been also found in this kind of the vanadium doped topological insulator. As I just told you, there are 2 systems with the zero field anomalous Hall effect. One is chromium, one is vanadium, but vanadium was unexpected from the theoretical predictions, but we can still realize the quantum anomalous Hall in the experiments. So, and also in this kind of the exfoliate manganese bismuth telluride 1-4 phase flakes with the order number layers, and more in the past 2 years, and the quantum anomalous C equals 1 quantum anomalous Hall effect at zero magnetic field was also realized in twist bilayer graphene system, and also in this kind of the AB stacked multi-cyanide and constant telluride bilayer structures. As I just mentioned before, we can see that in this kind of the magnetic TS system, when the longitudinal resistance is finite, the Hall resistance always lower than this kind of the H over E square. But we can see that in this kind of the twist bilayer system, when the longitudinal resistance is finite, actually this kind of Hall resistance is already greater than this kind of the H over E square. So I'm not sure what is this kind of the response to this kind of the phenomena. I think the more study and more twist this kind of the quantum anomalous Hall device are needed to clarify this kind of the difference between the magnetic doped system and twist this kind of the system in the futures. And in the quantum anomalous Hall effect, as I just told you, the chiral eddy state is dispenseless. But when you put this kind of the normal contact on the quantum anomalous Hall insulator, this kind of the contact can generate this kind of, when you take this kind of measurement, there is still contact resistance, and the contact resistance is usually H over C squared. C is just the chain numbers. So to reduce the contact resistance, we should increase the helical, this kind of the numbers of the chiral eddy state in the quantum anomalous Hall insulators. So let's compare to this kind of the C equals 1 quantum anomalous Hall effect and high chain number quantum anomalous Hall effect. In the C equals 1 quantum anomalous Hall effect, there is only one chiral eddy state. And this kind of, there is only one chiral eddy. When the electron travels from the chiral eddy state to the normal metal contacts, just like the cars from the highway to the downtown, it will take you a long time. So however, in this kind of the high chain number quantum anomalous Hall effect, there are several this kind of, there are a number of this kind of the chiral eddy channels. So this kind of the so it will agree if we put the normal contact on this kind of the high chain number quantum anomalous Hall insulators, it will greatly reduce this kind of the resistance between the quantum anomalous Hall and the contacts. So this is actually one advantage of the high chain number quantum anomalous Hall insulators. So next, I will introduce how to realize the high chain number quantum anomalous Hall effects. So here we construct this kind of the high chain number quantum anomalous Hall insulators by stacking the C equals 1 quantum anomalous Hall and the normal insulator layers. But from the MBE groups of the point of view, in the past almost 8 years, it's very difficult to find this kind of the normal insulator layers as a group to connect this kind of the C equals 1 quantum anomalous Hall layers. So here we take this kind of the heavily doped magnetic doped this kind of the TF film. We notice that the chromium doping, if you dope a lot of chromium in the TF film, the chromium doping will reduce the spin orbit coupling and drive the magnetic TI to the normal TI layers. But this kind of the heavily doped magnetic TI shares the same structure with the TI. So this is very helpful for the MBE groups. So this is the C equals 3, the high chain number, the C equals 3 quantum anomalous Hall effects. And this is the TM image of the heavily doped magnetically TI and TI heterostructures. We can see this kind of the very highly ordered lattice structure. And we systematically fabricate this kind of the magnetic TI and TI multilayer samples with periods from 1 to 5 and found that the Hall resistance of these 5 samples is H over E square, H over 2E square, H over 3E square, H over 4E square, and H over 5E square. That's just at the same time, and the longitudinal resistance is vanishing at 0 magnetic fields. So this observation indicates the realization of the quantum anomalous Hall insulators with chain numbers from 1 to 5 in these 5 samples. And actually, we can further increase these kind of periods. And recently, we could realize the very accurate this kind of the C equals to 10 quantum anomalous Hall insulators by my students. And the chain numbers of the quantum anomalous Hall insulators is actually, if you see this kind of the Lego structures, we can see that the chain numbers is actually depends on the numbers of the undoped TI layers in this kind of the multi-layer structures. And the realization of the high chain number quantum anomalous Hall insulators is further demonstrated by the gate dependence of the ferromagnetic field Hall resistance and longitudinal resistance. We can say that the Hall resistance quantized at this kind of the h over e squared to h over 5e squared, and the longitudinal resistance shows a dip and approach to zero at the charge neutral point. So this is actually demonstrated. What we observed indeed is the high chain number quantum anomalous Hall effect. And next, I will introduce how to tune the chain numbers in the same these kind of the sample structures. We found that the chain numbers of the insulator can be tuned just changing in this kind of the pentalayer structure, 5-layer structures. If we could tune the chromium doping level in these 3 layers, we actually can tune the chain numbers. And in this kind of 5 layers, for the chromium doping is 0.13 and 0.15, it shows the C equals to 1 quantum anomalous Hall effect. If you further increase the chromium doping level at the X equals to 0.25 and 0.235, we can realize this kind of the C equals to 2 quantum anomalous Hall effects. So as I just showed you, for the lower doping level, the middle magnetic TI layer is still topological non-trivial. So these 3 layers seems share the same topology. So there are only 2 this kind of the chiral, 2 non-trivial surface state, and one contributes h over 2e squared. So the total Hall conductance is h over e squared. So if you increase the doping level, this one will become topological trivial, and this is undoped TI layers. So you will introduce 2 more this kind of the non-trivial interface state in the middle. So there are 4 non-trivial interface states in this kind of the system. So the total Hall conductance will become e squared over h. So this is just the quantum anomalous Hall insulator with the chain number equals to 2. So the tuning of the chain number is also demonstrated by the gate dependence of this kind of the Hall resistance and longitudinal resistance. We can see that for these 2 and at the charge neutral point, indeed quantized at h over e squared, at the high doping level quantized at e squared over 2h plateau. So our experimental observation is well interpreted by our theoretical calibrator done by the Professor Chaoxing Liu, also at Penn State. And in addition, we also found this kind of the chain number of the quantum anomalous Hall insulators can be changing by the thickness of the binary layer. The changing the thickness is just changing the interaction between the 2 C equals 1 quantum anomalous Hall insulators. We can see that when D is 0 and 1 quintuple layer is h over e squared, this is just a C equals 1 quantum anomalous Hall. And when the D is 2 quintuple layer, 3 quintuple layer, and 4 quintuple layer, is C equals to 2 quantum anomalous Hall insulator layers. So when this is done, this will form the same C equals 1 quantum anomalous Hall effect. If this kind of the middle magnetic TI layer is thick, it will separate this kind of the 2 C equals 1 quantum anomalous Hall insulator. It forms this kind of the C equals to 2 quantum anomalous Hall effects. And this kind of the tuning of the chain numbers is further demonstrated by the gate dependence of the ferromagnetic field. We can see this is the D 0 and 1 quintuple layer is indeed h over e squared, and above the 2 quintuple layer, it shows the C equals to 2 quantum anomalous Hall effect. And this kind of the experimental observation is also interpreted by our theoretical calculation. So in the last 1 or 2 minutes, I will introduce our recent progress about along this direction about the chain number quantum phase transition. As I just told you, in the previously, we can realize C equal to 1 and C equal to 2 by tuning this kind of the chromium doping level. So we will think about if we systematically tune this kind of the chromium doping level, can we see this kind of the chain number change induced quantum phase transitions between the C equals to 1 to C equals to 2 quantum anomalous Hall insulators. And we will take a look for this kind of what happens for this kind of existed chiral eddy state of the the original C equal to 1 quantum anomalous Hall insulators and how to involve the one more chiral eddy state in the quantum anomalous Hall insulators. So this is the data. We systematically change this kind of the chromium doping level. We can see the Hall resistance monotonically decrease and the longitudinal resistance first increase and then decrease. If we summarize this kind of the ferromagnetic field longitudinal resistance and the Hall resistance, we can see that when the X less than 0.16, it shows the C equals to 1 quantum anomalous Hall. If above 0.24, it shows C equal to 2 quantum anomalous Hall. And this is just the chain number change induced quantum phase transition. And in this phase transition, we can see that the ratio between Hall resistance and longitudinal resistance is always greater than 1. That means the original chiral eddy state is always there. So that means the original chiral eddy state coexisted with this kind of the bulk conduction, during this kind of the occurrence of the quantum phase transitions. So here we come to the end with the summary. So we were the first to realize the quantum anomalous Hall effect in the chromium doped TI system, and we fabricated this kind of the magnetic TI and TI multi-layers and realized the high chain numbers. And we tune these kind of the chain numbers by tuning the chromium doping level and tune the thickness of the middle layers. And we also, in this kind of the by systematically tune this kind of the chromium doping level, we found that the chain number change induced quantum phase transition between the C equal to 1 to C equal to 2 quantum anomalous Hall insulators. So I need to thank my students and postdoc and also my collaborators, all from Penn State. And this work is supported by the DOE, NSF, and ARO, and the Moore Foundation. Thank you. With that.
Thank you, Chizu. It's a fantastic talk. Yeah, are there questions in the audience for Chizu? To get it started, may I ask a question? Here, when you add more channels to the edge, do you need to consider the correlation effect, the electronic interactions over there?
Yes, this is a good question, and you know that that's actually also the reasons we systematically change the thickness of the middle layers. If this is just there is no coupling effect between this kind of the 2C equals 1 quantum anomalous Hall effect, that's actually just parallel connections. So that's actually that's actually the reason I was asking my student to systematically change the thickness from from 0 to 5 quintuple layer to see the chain number change. And actually, for the MB groups, we can actually group the 1.2 and 1.4 quintuple layers to take a look at these kind of the phase transitions from the C equal to 1 quantum anomalous Hall effect to C equals to 2 quantum anomalous Hall effect. I think in this kind of high chain number quantum anomalous Hall insulators, the interactions between the C equal to 1 quantum anomalous Hall insulators is very important for the realization of this kind of the high chain number quantum anomalous Hall insulators. Yes.
Okay, thank you. Are there any other questions? So I don't see any, but we can continue the discussion by typing your question in the chat. We will come back to discuss these questions later in the afternoon. Okay. So now I think I should close this session, give everyone a few minutes break. Let's come back in 7 minutes, 12:50. Thank you.
La grabación se ha detenido.
All right. Well, it is
Esta reunión está
12:50
siendo grabada.
and time for session 2 of our meeting today. I hope you're all able to step out and get a bite to eat maybe, and that you can enjoy while listening to these next set of talks. The first speaker in this session will be Peng-Cheng Dai from Rice University, and he will be discussing spin excitations and superconductivity in uranium tellurium-2. Peng-Cheng, are you ready?
How long is the talk? I'm sort of, yeah.
You have 30 minutes
Okay,
until
okay,
1:20. So it'd be good to leave maybe 5 minutes for questions. So total talk time 25 minutes.
Great.